Now, I'm been told here that the microphone doesn't work. If it's too quiet, let me know. So we'll see. Okay, yeah, and let me know if it's too quiet or not. Before there are way too many mouth sounds. Okay, so I'm going to talk about Braille first in this part of the music encoding. So I have these technical terms up here. I'm just going to try to make sure I cover them. Louis Braille lives in the 1830s. He is a monk. He made Braille notation for text, which is what you see by elevators and bathrooms and various other places, but also for math and for music. And the music Braille is kind of an odd one because, of course, it subsumes all the others, right? You have text in music, and you also have numbers and numerical things in music, so you got all of them. Okay, so the music Braille is rather complicated, but the part of the music Braille that we will look at are just the music symbols. And then there's special cells, or Braille characters, which is called Braille cells, that indicate when you're switching to text or when you're switching to math or numeric. You know, you can get a free coffee drink downstairs if you... Okay. But if you do get one in the future, get an expensive one so that they get well supported down there. Okay, so anyway, so we have these things. What is a Braille embosser and a Braille cell? A Braille cell, like I was saying, is a character, Braille character. It's got 6 bumps in it, or 6 positions, and you can see here on your handout there are some light bumps and some dark ones. The dark ones are the ones that would be embossed or be pressed down, and then the light ones are just the other blank positions so that us sighted people can read this stuff well. So here's something I would normally pass around. See if I can, sort of hard to see, but this is embossed Braille. A Braille embosser is a printer. And it's really loud because it's really mashing down the dots. This is printed single-sided. Normally Braille is printed double-sided, but it makes it even harder to look at on an overhead projector because you've got pits and bumps. So when you're feeling, you ignore the pits, you just go for the bumps. And anybody can feel these patterns, although normally what I do is I pass these around, and only very few students can actually tell what they are without any, getting used to it in training. But it's just like if you want to do the long live and prosper, anybody can do that, but the first time you try, your fingers don't go the right way. So it's sort of like that. So these are the Braille cells. As you can see, there are 6 dots in a Braille cell, or 6 bits for us engineers. So there's not a whole lot of, it's not ASCII. There ain't 7 bits or 8 bits, depending on what you think of ASCII. There's only 6, and it's encoding a lot more than just basic text. Music is a 2D notation, printed sheet music, as we had looked at optical music recognition and in the homework music typesetting. Those are, it's a 2D notation. There's a lot of issues about 2D notations. Braille is very different, right? It's a 1D notation. I mean, it's like text. And every object is an island. There's no interconnected things. So in some ways, it's way simpler. On the other hand, music notation has made it all around the world in a pretty standard format. And it's quite useful, despite some weirdnesses about it. So Braille is interesting. Like so many things like this, a Braille musician can actually read music faster than a sighted musician sometimes. And other times it's way worse. And certainly one big restriction in Braille is that, say, you're a trumpet player, you can't be reading your Braille while you're playing trumpet. So, there's quite a few practical differences. All right, so the Braille cell. So a Braille note cell is actually, it's on the next page, and I'll want to tell you about it. And I want you to actually sort of know about Braille note cells. The rest of this, I'm just giving you a quick survey of it. I spent quite a few years working on this, and working for a boss who was unsighted or is still unsighted, and it's an important thing. So I just want you to know about it, and take it seriously, just like sheet music notation as a notation. So Braille note cell, it has duration dots and pitch dots. We'll talk about that next time. One of the things about Braille is, well, he was a monk, and the main kind of music he was doing was Gregorian chant. So this is this notation that, I mean, he did great work, but unfortunately, it's the notation is very much optimized for Gregorian chant. And yeah, that's nice, but Gregorian chant is quite simple compared to a lot of the counterpoint and other music that we have. So it is one of these things that has a very simple, nice core, and then all this complexity built up on it. And not totally ideal. It turns out because of that, even though sheet music notation is quite standardized throughout the world, that's not true of Braille. Braille is, has variations. They're not huge variations, but it has significant variations depending. There's U.S. Braille and U.K. Braille, and Braille from the various countries. Yeah, so there's various varieties. So in a single Braille cell, you're notating both the pitch and the duration of the note. Now, given that you only have 6 bits, we'll talk about that. But then there's several other Braille signs, or special Braille cells for octaves, for rests, for clef changes, for accidentals, for key signatures. So I'll show you a few of those. You don't need to know any of those, but I just sort of want you to know how the system works. For those of you who are used to are familiar with Unicode, like UTF-8 or something, it's a bit like that, right? You can extend your 8-bit thing to be 16 or any multiple of 8 bits by encoding things, and that's the way the Braille cells work. Items in Braille can be quite long if they're rarer items. And okay. So for simultaneity, this is a big issue. In 2D notation, you can write things above each other. And there's a lot of different ways to do that. Like sometimes you have multiple voices on a single staff. Sometimes you use several staves in a system. There's all sorts of different things that you can do in, or sometimes you'll use 2 staves for 3 voices, like if you look at 3-part inventions or something. There's all sorts of varieties of ways of doing it. Well, in Braille, it's problematic because it's a linear notation. So you don't have the 2 dimensions worth. So there's a lot of different ways they have. Sometimes you have interval marks. Sometimes they have inaccords. So if you have like parallel fifths or something playing, then you have a very efficient way of saying that. You have a bar over bar notation, where you actually do have the same bar written physically, the Braille for it, for different lines above each other. You have section by section things. You have all sorts of things. And since Braille requires you to, at least if you're, playing trumpet or violin, it requires you to have memorized your music by the time you're playing. There's a lot more of, well, what can you on first reading easily remember? And how do you get a good oversight? So it's up to the Braille embosser. We have different issues than in the music typesetting, but whoever embosses it does have a lot of decisions of how do you make this most readable, and especially on first sight reading. All right, Music XML has information that's really important for Braille music. And so I talked about Music XML. Now, Music XML is not the only interchange format. It's just one of the leading ones. It turns out it's sort of a counterexample to the committee-based standard stuff, because the committee-based standard stuff in music just kept getting stuck in the mud and didn't just pick something and do it. So for Music XML, is a company that owns it. And for this homework, you're going to read a short intro to it and learn about it. And I think they've made some mistakes in their decisions, but they've made decisions, and that's really, really important. If you have a standard, it's just got to be set. What is the standard? And however imperfect it is, English spelling is pretty imperfect. That OUGH can be so many different things. It's kind of dumb, but hey, it's a standard. And lots of people have tried to change it, and realistically, there's bigger problems in the world. And just having a standard, even when dumb, is good to have a standard. Okay, so yeah, music XML and other interchange formats like that are super important because it's information that's not in MIDI. And even though Braille is a 1D notation, still it needs all that information. It really does encode the same sort of information as you have on the page. There's some funny exceptions, like for instance, Braille text doesn't distinguish between uppercase and lowercase letters. Okay, but that's pretty minor. Mostly what you see on the page is really there. And yeah, since, as I say here, since music XML, since almost everything is prepared on computers nowadays, it's a huge deal to have an interchange format so that then you can take whoever prepared the music, wherever in the world, you can take that music and have it embossed in Braille if you go through a program to do so. It's not a trivial process. It's semi-automatic usually because there's decisions to be made about how do you best go from this to that. Okay, I can't pass around the Braille example because COVID. So here's a question. Why bother with Braille music? I mean, traditionally what happens is, say you're a grade school teacher, in some district somewhere, and being a music teacher, you're somewhere low on the pecking order, to put it nicely, and you've got a blind kid who's learning to play violin. Well, the obvious answer is just play by ear. The thing that's weird about that is, if you were a teacher and you told a sighted kid that was learning violin, just play by ear, you'd be fired. That'd be it. End of story. But somehow it's totally acceptable, if they're blind. Yeah, so if possible, one of the things that I was involved in was to try to also make tools for teachers who are already overloaded. Like, how do you even deal with this? It's not like a music teacher has lots of other free time. How do you make it easier for them so they don't have to, go to school to learn Braille or something, so they can easily do something with helpful computers. But anyway, why bother with Braille music is a serious issue. I'm very proud to say that software that I contributed to is responsible for the majority of Braille music in Library of Congress, which tells you two things. One, we printed a lot of Braille music. And two, there wasn't a whole lot of Braille music in the Library of Congress to begin with. So both of those are true, but I do think it's an important issue. So a little bit more about the nitty-gritty of Braille. Here's a Braille music cell, and I sort of want you to know this. You don't have to memorize all of this, but you have to. I want you to know what a Braille music cell is, because knowing just any part of it, I think, is good just to start. So you've got 6 dots. C, D, E, F, G, A, B. So across here is the pitches in an octave. First thing you notice is, well, what about C sharp? Well, it's kind of like standard notation in that way, right? If you have a C sharp, there's an extra symbol for the sharp. Or either that or you're in a key where it's implied. First, so you have the just the note names within an octave in this direction. And if you look at these Braille cells, you'll notice all the C's, the top 4 dots in the cell, are the same. All the D's, the top 4 dots are the same. E's, the top 4 dots are the same. Right? So the top 4 dots are telling you the pitch. And then the bottom 2 dots are telling you duration. Now, in 2 dots or in 2 bits, you only get 4 different values. Well, that's plenty for Gregorian chant. Turns out it's not plenty for other things. So what happens is the duration dots, the bottom 2 dots, are the same symbols are used for whole notes and sixteenths, which seems like it could be incredibly confusing, but most of the time it isn't. Just like in standard notation, you have bar lines, and just like in standard notation, I've played now I'm not a great musician, but I've played plenty of orchestra music where there's just all this black on, all these notes, and they had to be done in this beat. You could just tell by looking at the music. And I didn't know if those were 27 or 28 notes or however many there were. I just played something and tried to get at the end. And a really good musician would actually have subdivided properly. I did something. If I hit the right pitches, I was lucky. But in any case, you can just see overall and get it done in time. Similarly, when you have quintuplets versus sextuplets and things like that, in standard notation, sometimes they'll print the little 5 and the little 6 above it, but a lot of times, after a while anyway, they just stop doing that and they expect you to be able to see the pattern, and it's okay. So the same thing happens here. Normally, it's just not that hard to tell the difference between a whole note and a 16th, or a half note and a 32nd. So there is this real question, though. Why did Braille use this encoding? Right at the very beginning. Well, it's super efficient if you're doing Gregorian chant, right? Almost always, every note is just one cell. Now, if you're not doing Gregorian chant, it's kind of complicated, but it's not that bad. It's kind of like English spelling. It's dumb in some ways, but it turns out it's workable. And so everybody keeps it. I don't know of any Braille notation that strays from anything this basic. All right, questions about that? So I want you to sort of know what these cells are. Just for interest, you have octave signs. For instance, all of these are C's. As you can see, the second character here is always the same, well, except for the A. But so there's C's here, but then there's an octave sign before it. You only need the octave sign when you're switching octaves. So you can just leave it out. It's implied to be the same octave as previous. Octaves start on C, just like they do in Midi, just like they do in MusicN, just like they do in lots of places. Just like they do on keyboards. I mean, I don't know why they start on C and not on A. Why do the names start on A? And I don't know. It's historic. It's the way it is. You got major, minor, and you got to pick one. So anyway, they all start on C, and then you can see the simple pattern here. Not all Braille is just easy to remember, but look, the lowest notes are at the top dot, and then you move downwards. As you go down, that's kind of cool. So it takes one Braille cell to select octave, but then if you look at clefs, it takes 3. But that sort of makes sense, right? If you wanted to try to efficiently encode something, well, clef changes are rare. They happen at the beginning, and it's rare to have them happen in the middle of the music. So the clef changes are multiple symbols. Rests, again, are single symbols and have the same ambiguities. It's really just a special pitch for the rests. All right. What else? Other little tidbits. In our standard music notation, sheet music, we use 2 flat symbols for double flat. Just, sort of repeat it. We run them into each other a bit. But actually, for whatever reason, we don't do that with double sharps. And in Braille, they just use 2 sharp symbols in a row. Not too amazing. For key signatures, they did the same thing that you do in music for sighted people. But I should say sighted and unsighted, right? A dumb person just means somebody who can't speak, but of course, in common use, that's not so good. In a blind person, of course, means somebody who's clueless or doesn't know anything about the future or something like that. Although most blind musicians and blind people I've worked with don't really mind the word, but there's sightless and unsighted is sort of a more politically correct, although I don't know if that's the current word. Anyway, I have a great story about that. There was a video now this was like 20 years ago or so. There was a video that came out and was on YouTube and various other places and showed on TV that explained how you should deal with unsighted people. Because, especially in areas where there's schools for the blind and such, there's a lot more blind people around than you'd see here normally, and people want to run and grab them and steer them different ways and stuff. They don't realize that if you really learn to listen, right, you can hear all sorts of things. You can hear the reflections of sound from trees and from other things, or the wind shadows if it's breezy. So it's and people know their routes, and people like to be independent. So there's sort of this video about, have understanding for blind people. Don't just run up to them and do things for them. You ask them first if you're gonna and people like to be independent. So anyway, so they saw this video, or they heard this video, and so they made their own spoof video of it about So they had light dependent and light independent were their words, but they had this video for light independent people explaining, well, for light dependent people, they have a lot of unusual problems, and you should have understanding for them. They're proud of what they can do, and they're not, you certainly don't want to be demeaning, and you also don't want to like always jump in and try to help them. But like a light dependent person will walk into a room and if it's dark, they get scared. And you have to have understanding for this. I mean, it seems kind of weird, but, it just went on to explain all these different things that light-dependent people have trouble with and that light-independent people. Anyway, they have a sense of humor. They're not that uptight. Okay. Data notes. Yeah, all these things. And then there's something about, stuff about simultaneities and interchords and stuff. We'll not go into those details, but I just wanted to give you an idea of what Braille is. It's out there, and these interchange formats are super important. And it's very important to remember these things because there's all these efforts like for PDFs or something, to make PDFs so that they can't be altered, they can't be read by other programs, they're really secure and stuff. Well, that's great, but what if you're an unsighted person trying to use a computer, trying to read this stupid document? Well, because of somebody's security paranoia, right, the document's not readable to you and stuff. All these things come up over and over and over again. So it's really important to remember, hey, there's people out there for whom your decisions really matter, and to consider those people also. Here's a good question. How popular is Braille music, and how many people use it? Well, actually, it is a real problem, right? Because it's getting better now, and any music, just like in schools now, if you learn to read music, or at least rudimentary read music in school, or certainly if you play in band or orchestra, you learn to read music, and all those people are learning Braille nowadays. But it used to be, not that long ago, that very few blind musicians knew Braille, and one of the reasons for that was that there wasn't very much Braille available. So there was really not that much reason to learn it, and for people to produce it well, since musicians are doing fine without the Braille. But that's the same thing for sighted musicians, right? You have some very talented sighted musicians who don't read music, and then a much larger set of them, especially in pop music, that claim they can't read music but are actually, I've met so many of the rock and roll heroes where I was amazed that they weren't dead from drugs or from some other debauchery. But the other thing is that they were classically trained and incredible musicians. They just don't tout that on stage because that's not what makes a cool rock and roller. But actually, there's a lot more trained people out there than you think. But yes, for Braille, it's increasing a lot, but that is an issue. Like, how many people really know Braille? And I would say now, if you are a young musician, going to any sort of organized school, and you're blind, you'd be learning Braille. And there's enough of it out there now because there's enough concerned people. It used to be that, there were monks and other groups that would make it their business to produce Braille for you, but it's a slow process. Say you were in college and you were, studying some symphony for some class. Well, if it takes 2 years to get the Braille for that, that's a problem. And so now that's, I think it's getting better. But it is a real issue. How many people know it is a real issue. Bless you. Another group that's really growing now, because we worked on these things for teachers of blind musicians. So we had a setup where there'd be standard notation, high-lit, with a whatever note is selected. But then the associated Braille was also high-lit. So if you knew either notation, you could sort of see what the other notation is. Well, if you could see, and so there's also a growing group of people now that are going blind and know they're going blind, and they learn Braille before they go all the way blind. And there's better tools to do that. So that's actually a pretty good percentage too of people that are out there doing this. In general, people that are really totally blind in the U.S. It's quite a small number, actually, compared to, other populations. It's not millions of people or anything like that. And so in that way, it's a small enough community that the fact that we have Music XML in an automatic way to get Braille, even if the Braille isn't perfect, is a huge, huge deal. Okay, I think that's the best answer I have for you. I don't have real numbers, but I could find out if you are interested in that. There are other issues with Braille that are problematic, like Braille Displays. So a Braille display is a thing you hook up to your computer, pushes up little bumps. They're insanely expensive. And like a really good Braille display is still at 80 characters. That's as if your screen had one line that was much shorter than one of these, And that was supposed to be this great thing and cost a boatload of money. But the problem is it's a mechanical system, right? You're really pushing up these things. And so, yeah, someday somebody in materials is going to come up with a very cheap way to do this. But so far, that's not happened. And every few years I see patent for this or that, but so far I haven't seen anything. If you do know of something, I know people wondering. So if you do see anything like this in the future, please let me know. All right. So next, I want to talk about MusicN. MusicN is in the homework. You're going to see more of this. This is just a short help with the music. MusicN. Max Matthews at Bell Labs started this, and he called it Music 1, and then he called the second version Music 2, and the next one Music 3, so he just put an N after it. And then later on the IBM 360, for instance, there was Music 360. But it's just a framework. When I say just, that's super important. I mean, heck, the web is just a framework too. But it's a framework for being able to compute samples and sharing algorithms for that, writing scores and that sort of thing. So Max Matthews, become the father of computer music since he was the guy that started this stuff. There's an idea of a score. Now this is yet different than Braille, and it's yet different than MIDI, and it's yet different than sheet music. It's a series of data statements. And so C is just a comment line, I is an instrument line, and then it says the instrument number. The comments here are telling me this, the start time in seconds, the duration in seconds, the pitch in this octave.pitch class thing, which I sent you email about too. So if the reading doesn't make sense, please look at my email. The email also has a link attachment for the Music XML part of the homework that'll save you some messing around, possibly. So go ahead and look at that. Then there's other parameters. They can be whatever you want, actually. And you'll see how that works. But these are just data statements. So this is a very thin layer over what's underneath. In a lot of ways, the Egan matrix is like that too, right? You're putting these formulas in different places, but you can kind of tell, well, this is just a filter, or this is just a this, or this is just a that. It's fairly simple objects that you're connecting together in this way. There's a different way of doing it, this with the score. So in that way, it's very traditional. It's like, you have an orchestra and a score. But you can use it in very non-traditional ways. I mean, these events don't actually have to be notes. They could be lots of other things. So you can use it in a much more generalized way than what was in here. So instruments are numbered. They're defined as interconnections of basic blocks. Or you can call these blocks, hey, if you're a programmer, subroutines. Or, subroutines in a library. But basic blocks called unit generators. Okay? For the pitch here, again, this fourth octave pitch, 4.00 is a C. Right? 4.09 is going to be an A. It's just a ninth half step. What is 4.051? Well, it's a fifth half step and then a tenth of a half step or 10 cents above that. So you can put fractional numbers there if you want. People sometimes do. It depends what kind of music you're writing. But these aren't really decimal numbers. So be sure you catch that. Why don't you ever see 4.37? Again, it's because 4.11 or 4.11, I should say, point might be misleading. 4.11 is the B, and 4.12 would be the C of the next octave. You just write 5.00. So anyway, you'll read more about that. So people used to like to do these diagrams a lot. You still see them an older system. I mean, I like to, you know, show diagrams too of electronics. I don't know. These diagrams never did anything for me. I just thought they were kind of confusing and silly. But you can still buy templates for them and draw your diagrams. There are lots of modern versions of this. Like you've got C music, you've got, you know, all sorts of variations nowadays that are still very much in use. And, you know, what is cool about this compared to a DAW? Well, if you want to play on your Midi keyboard and record lines, then listen to them back and add reverb, this is not for you. But if you want to, you know, have some algorithm that, for instance, makes a score, or you know, or whatever, you know, there's various compositional styles that are sort of semi-automatic. It's great for that, right? Where so just because it's text-based. Okay, so I'm going to show you here the three core issues here in the instrument definition, or in the orchestra definition. So this is one instrument that's being defined here. There's three main subroutines for each instrument definition, and you really do set these up. The first one is a one-time initialization. Happens when the program starts up. In this case, this is a really simple sine wave oscillator based on table lookup. So what it's doing here is just computing the sine. And the only reason it does this and sticks it into a memory table is that the sine function is sort of expensive. When you're computing every sample, if you don't need to, don't evaluate a sine. That's just going to slow everything down. You know, this, of course, was done on computers that have much less processing power than your toaster does now. So it mattered back then, but it still matters now. If you want enough voices, you know, if you want to make thousands of sine waves or something in real time, yeah, you know, might as well set up a table if you can get away with it. Some applications, a table really isn't the right thing, but usually it's good. Then there's a tone set, as it's called here. What this is this is really just reading the parameters out of the score. So the framework will go and, you know, MusicN language will read up this line. It has a instrument number, so it knows what subroutines to call. It has a start time in seconds. So if it's time for your thing to start up, the note to start up, it knows that, and then it has a duration there in seconds. So it knows for how long does it call these subroutines. Well, the first time it calls it for one of those I-cards, for one of those instrument lines, what all this is doing, these P things here are the parameters from the instrument line, and it's just stowing them away, squirreling them away. A few of them, it's here it's computing a frequency from the pitch number, you know, from that weird octave.pitch thing. But basically, it's just saving all these things. There's a few funny calculations here. These are details that you really find out are actually sort of a hassle when you use this. One of the things in the MusicN languages, the note decay is included in the duration. And the reason that's true is that the framework has to know for how long is this going to generate samples. Because it doesn't really know what your subroutine does. So you have to tell it until it's all the way decayed out. So if you have an exponential decay that lasts 2 seconds, you have to be real careful about your duration times and stuff. It's actually sort of complicated. On the other hand, if you think about it, well, the system has to know how many voices, how many notes play at once. And from this, you can tell. Right, if you look here, like how many notes are in this example are playing at once? Well, at start time 0, you have a duration 1. So that lasts for 1 second. At a half a second, while that one's still playing, you have something that lasts a second and a half. So you can tell, and then at 3/4 second, you have another one. So there's at least 3 notes here playing at the same time. You know, you can go through and really check. But there or 3 sets of subroutines that are still generating samples. So there's this tone set, which is done once at the beginning of sorry, brain off. There's this tone set, which is done at the beginning of each note or each event. And then there's a tone samp. This is sort of the thing that you try to optimize. And usually, you're just calling routines that somebody else already optimized, these unit generators, with parameters in them. And, you know, the capital N here is which voice number it is. Or do they call it instrument number here? Instrument number, I guess. And that sort of thing. So you don't have to know everything about this. The point of the homework actually is that 2 things. One of them is to just sort of have seen this stuff. You are extremely unlikely to use exactly this in the future. But things like this exist in many, many places. And so I want you to have seen it. It's sort of a historical interest, but it's also one of the things you're doing here is you're going to compute start times based on a changing tempo. And what you want to do is figure out yourself a formula. Now, if you know the MusicN languages already, don't cheat, you musicians out there or you music majors that know this stuff. Don't put tempo lines in there. That's cheating. You're supposed to actually compute the note durations and not have it do it for you. Yes, the languages actually support ways of doing tempo changes where you don't have to compute all the details. But no, I want you to compute the tempo changes just so you can see it. Much like when you do a vibrato, if you simply just change in hertz linear, it sounds like a siren. It doesn't sound like a vibrato. It's not the right thing to be doing. And the same thing with tempo changes. If you just do, a linear tempo change, it doesn't sound right either. All right? Questions about that? Good. All right, so then the third topic that I want to start today, we're not going to finish it today because it's a bigger topic. It's a bigger topic, too, because MIDI is the way that, I'm going to talk about MIDI, and MIDI is the way that, the main way that synthesizers communicate with each other than the method of the day, which right now is also USB. But even over USB, much of this material is exactly the same. And there's endless confusion about MIDI. There's always people that are designing new versions of it, including the MMA, the MIDI Manufacturers Association, making new versions of MIDI, and they don't solve the previous problems they had. People don't know what the problems are. Just because you're on some committee doesn't mean that you actually understand the issues. And it's sort of an unfortunate situation. MIDI is, I have a love-hate relationship with it. It's actually extremely cool that it exists, and it has problems that could be resolved, but come from many different sources and are usually misidentified. So I want to talk to you about it. Another reason I want to talk to you about MIDI is something even very simple. Look, you're engineers, or most of you are engineers, and it's sort of embarrassing if you don't know this. I mean, a musician would expect you to at least understand this, because this is, hey, there's electrical engineering for you. There's wires, cables, and UARTs and other components. You should know what this is. So I'm going to talk to you about MIDI, and I will have plenty of complaints about MIDI, but it's actually, even in its current form, even with its shortcomings, it is quite useful. It's just unfortunate how many problems we have that could be so easily avoided. And then how many solutions we have that are, a really big hammer to solve something that, solves some issue with MIDI, but then doesn't solve all the other issues with MIDI. All right. So first thing I want to talk about is a MIDI hardware interface. This is the original drawing from the original spec from the 1980s, and it doesn't have vacuum tubes in it or anything. You could understand it. I would suggest you redraw it. At least I did for myself. So that's what I scribbled over here. If you are here, if you're online, you can just copy the frame or stop the video. But if you are here, you can take a picture of this afterwards. I like to redraw the thing because this is okay, but if you redraw it yourself, now when you copy mine, you didn't redraw it yourself. I would say, hey, why don't you redraw it yourself in some way that you like. Just put the component somewhere else so you're actually understanding what's there rather than just looking at it and trying to instantly absorb things. But lots of different words for MIDI. Do you guys know what a UART is? I don't know if you've had 385, right? In 385 it comes up, or maybe even before then? Okay, so a UART just stands for Universal Asynchronous Receiver Transmitter. All it means is it does this kind of communications. MIDI is the same kind of communications that were used for typing keyboards, like key sets, as we used to call them at Plato, but unfortunately keyboard is the same word for music. But, these things, typing keyboard, back at the time. In fact, they used the same connectors back then, too. So if you're into retro stuff, you'll definitely recognize Midi cables. I will show you some Midi cables here. So a Midi cable has this kind of connector on it, which, as I say, was really common with computers back then, and held ASCII data. Would transmit ASCII data, which was also transmitted over UART. And really all MIDI is the same stuff. Use the same cables, use the same UARTs, use the same everything, but go at a different rate. Back then, a communications that went at 1200 baud was super fast. We did that here at U of I because we were nuts. But normally it was 100 baud or 300 baud. MIDI is 10 times or 30 times that. It's 31.25 kilobaud. So it is super fast at the time, but they just realized, this is the minimum you need to really do music. So there were people involved that were super smart. Not all of MIDI is dumb. And now people still think, oh, it's way too slow. And they're almost always wrong. Almost every last case of people claiming MIDI is slow is misidentified. Now, you can come up with test situations, right, with weird corner cases where you can prove it's kind of slow, but if you do real blind tests for listeners and stuff, it's always from somewhere else. And if you do a real blind test and don't realize where your delays are coming from, that's different. But there's all sorts of confusions now. Like people think that USB MIDI is faster than this, and just totally wrong and incorrect stuff. But people think they hear something, or somebody told them this on a I don't know. Anyway, we'll get to USB MIDI later. But there's 5 pins in there, and actually only 2 of the lines are used. And in fact, they hold the same signal. So it's not the same as differential. It's a current loop, but the same idea as differential. It has really good electrical characteristics. Or if you're more musically inclined, same as balanced. But it's defined in a different way. It has the same advantages, but it's a current loop. And we'll talk about the current loop in just a second. The biggest advantage it has is that you don't connect ground to ground. Just like in any good audio setup, right? You have an audio cable, but you don't connect grounds at both ends. The grounds only connect to one end for the shield of the cable. Similarly, here, there is a shield in the cable, and it's only grounded to one end. But there's 5 pins on there. You're only using 2 of them. Well, maybe 3 of them, because 1 pin does connect to the shield. That's not strictly speaking necessary, since you could have a contact on this metal shield, but not every connector has a metal shield. They wanted to be sure about it. So, so you have a pin that's dedicated on one end to connecting to the shield. Why does it have 5 pins then? Well, the friction is nice. That's really all it amounts to. It's a common connector, it's cheap, and friction is nice. And at that time, it was considered a miniature connector. Nowadays, unfortunately, it's thicker than your laptop. So no matter what you do, you ain't going to put this on your laptop. So that's the MIDI connector. Then there's lots and lots and lots of adapters. There's, of course, USB. And there's cables like this one, where on the one end, they have MIDI. And why are there 2 MIDI connectors? Well, because MIDI is unidirectional. And at very first, it's expensive stuff to make and stuff. It's a super high-speed communication for the time. And it was expensive to make. And, if you have a keyboard, it just tells the synthesizer what note's playing. And then that got fancier and fancier. And nowadays, there still are some keyboards that only have a MIDI out, but it's rare. Usually they talk both ways. If nothing else, most keyboards have a rudimentary synthesizer inside them, if nothing else. Anyway, so there you go. So that's MIDI in and MIDI out. And then this thing has a bump in the middle with a little brain in it. This is already quite old by now. This is from the 90s. But it's got the USB there. So this is a USB MIDI converter, right? And so if you have equipment that has this kind of MIDI connector on it, then you need a converter like this to get it into your computer. And, well, now usually you'd see it with USB-C, but same idea. Same speed, same idea, right? USB-C is a special connector. It doesn't change speed or anything. And this sends MIDI data, same rate that it goes over the other cables, with a few of the optimizations cut out. So it's actually a little bit lower performance. So, but not significantly lower. So anyway, that's what a USB MIDI cable is. All right. But we're going to talk about the real MIDI cable, not USB in the middle. USB is very poorly suited for audio. The first problem is that it has ground connected to both ends. So if you have any analog audio signals, you always have ground loop problems, and you have to put in isolators and all sorts of things. USB is a non-starter for music, except it's used everywhere because it's cheap. And, you know, everybody has a USB connector. I mean, if you make a modern synthesizer, you want a USB connector on it just because you want it easy to connect into your computer. So it is everywhere. And really, of these big USB connectors or the 3.5 millimeter version of it, only high-end synthesizers still supply those, because high-end musicians don't want the problems of MIDI, of USB. You know, they know that they want the real thing. And the fact that it costs a little more, it doesn't matter. Also, people that do analog synths generally stay away from USB. Again, because you have analog signals, and they get totally dirtied up by the lack of careful grounding in USB. Okay. So, what are some technical terms here? I talked about universal asynchronous receiver transmitter. It basically puts bits out on a line. You tell it, hey, I want to send this byte of data. And it sends out a start bit and a stop bit. We'll talk about that in just a little bit. And why is there a start and stop bit? Well, that's the asynchronous part of it. Universal asynchronous. Asynchronous means that the line is just dead and sits there if nothing's being sent. But, for instance, if you're typing on a typing keyboard, at that time, you'd press a key and then something gets sent. And the line would not be dead for a second. That's not true of USB, right? USB is always doing something. But back then, you know, the line was just dead until you press. So before, when the line comes alive, you have a start bit that says, hey, data's about to come. Then there's 8 bits of data, and then there's a stop bit, or 2 stop bits. And we'll talk about that a little later. But that's what universal asynchronous receiver and transmitter goes. So universal means it goes at all different rates. Asynchronous means that it deals with the dead lines. Receiver and transmitter just means that the chip that you get does both in and out. Okay, OC is open collector. Now this actually means something more specific than the way it's used here. All we mean here is it's the same as tri-state for those of you who have done electronics. The outputs are either low at ground or some sort of high impedance. And open collector means a specific way of making them high impedance. We don't actually care what the technology inside the chip is. But instead of being an output low voltage or high voltage, you have an output low voltage or an output that's the same as disconnected. So that's, you know, in the good old days, there were wire OR technologies and all sorts of things that you could do with this. Nowadays, this is used, but not so much. Main thing it's used for is we call it tri-state. So some chips can do low, high, or disconnected. But open collector and all of these things we're talking about here just do either low or disconnected, and we'll see how that's used. But when it's high impedance or disconnected, I call it high impedance here, low or high impedance, then it means that's not a high signal level, right? That just means it's as if, you know, it's high impedance as if it's disconnected from the circuit. All right. So MIDI, what does it stand for? Musical Instrument Digital Interface. There's the idea of a MIDI controller. That's the person sending that would have this circuit in it. And maybe a receiver too, if you can configure it and stuff. But here, you know, it would have the sender circuit in it, which I also redrew here and myself just so that I could understand it better. There's a Midi synthesizer. Well, that's a receiver. Again, this top part here is the receiver circuit. In between this top and the bottom here, from this guy to here, or from this 5-pin dude to that 5-pin dude, you have a cable. Okay, so the pins 5, 2, and 4 are, well, actually only pins 5 and 4 are connected to pins 5 and 4 up here. One of the things you'll notice right away in these connectors is somebody had incredible inspiration when they numbered these connectors. Right, connector numbering is a pain anyway, because you never know, are you looking into the connector or from the back of the connector? Because when you're plugging something in, you're looking into it, but when you're soldering to it, you're looking at the back of it. So connectors are confusing to begin with, but then why number the pins in order here? 1, 4, 2, 5, 3. And it gets worse. About 15 years after this brilliance was made, somebody at the main company that makes these things decided, oh, well, I'll simplify this. And they called them 1, 2, 3, 4, 5. So now it's like a total mess because you don't know which numbering system is being used or what. It's just, oh my God, what a mess. Yeah, it's unfortunate. You got to quadruple check whenever you do anything with MIDI for this reason. But anyway, the reason this numbering came up, in case you care, is that originally they had a 3-pin connector. They had 1, 2, and 3. And then they said, oh, okay, well, let's add 2 more pins. And they just thought, well, we'll leave those where they are, and the extra, and somebody made some decision. In the end, it doesn't even matter that much. The worst thing you can do is when you have a dumb standard is to make it non-standard by numbering it yet different. Anyway, so you have these cables here, sender and receiver circuit. So the MIDI synthesizer is this, but the MIDI synthesizer might be a digital audio workstation, or might be a piece of software, is what I'm saying, right? The MIDI sender might be a digital audio workstation. The MIDI sender might be a timbre editor. So it doesn't, from very beginning, the sender is sometimes called the controller or the keyboard, and the receiver is sometimes called the synth, but it doesn't really have to be that. It could be lots of different setups. So to repeat again, MIDI is often used bidirectionally. And when you have USB MIDI, that's just sort of automatic. The cable does both connections. But when you have these individual cables, you actually run 2 separate cables. One for one direction, one for the other direction. All right. So a current loop and optical isolation. I want to talk about that a little bit. I'm going to go with my little diagram here just because, hey, okay, I'll point it out here. So in this thing here, 2 things I want to point out. And I would label this on your notes too. This is the start of the current loop here, this 5 volts. Okay? And this is the end of the current loop here, this output of Mr. A here. Now A here is an open collector dude. So it can only be either low or unconnected. It's just something to know. I don't even know what A stands for. I forgot. But anyway, it's open collector. Why are there 2 inverters in a row? I have no idea. I think at the time, maybe nobody made an open collector that's non-inverting. I mean, they're totally available. They have been for a very long time. I don't know what the deal is there. But anyway, they have 2 of them in a row. Yeah, so, well, and only this one says A. This one here would need a pull-up resistor or something there. If this were open collector, the circuit wouldn't even work.
I think A is another term for like gate.
Oh! Yeah. Oh, it's like from the analog gain thing. Weird. Okay, there it is. Somebody knew that. Hey, I've never had a student who knew that. Yeah, A means gain in that case. Okay, so in any case, this is talking to the outside world, and this is, so the current loop begins and ends at the sender or at the controller. Well, that makes sense, right? I mean, it's a loop, right? A loop comes back to itself. So that's something to know. Another thing to notice here is pin 2 on here. This is just the ground symbol here, and it's sort of indicating that within your circuit, well, especially in the good old days, you'd have actually a pretty long cable within your device going into the connector, and you should use shielded cable there. Nowadays, usually this connector is mounted right on the board, and that's not really an issue. But what is important to note here is that pin 2 is connected to ground, only on the sender. On the receiver, it says NC, which means no connection. So the receiver, of course, has its own ground. Every circuit has its ground, and the receiver internally, if it has any cabling, should use a ground shield for that cabling, but it uses its own ground for that. It's specified. You do not do, the ground that comes from the cable does not go anywhere else. Hey, can I call you back in about an hour? Thanks. Okay. Yeah, it's always funny when you get a phone call and there's this long delay, and you can tell they're saying, "I'm not used to being told that I'm not going to talk to you now." Anyway, yes, very good. So we got current loop, optical isolation, those two things. We talked about, I'm going to talk about the optical isolation now. So the current loop here from this guy here, this is, again, the same as this A guy here. I'm just saying open collector here. It's not inverting in this case. But from the UART, it has a high signal or a low signal coming from the UART. And that's a normal voltage signal coming out of UART. And if it's low, then this part right here is grounded. If it's high, this part here is like it's unconnected. Now, because of the way this is set up, see pin 4 here, which says is current loop start here, there's a resistor to limit the current to about 5 milliamps. There's, and again, 5 milliamps was very little back then, and is a lot now, so most MIDI actually doesn't have that much current. But anyway, there's a current here that goes to pin 4, goes through the cable. Okay, so if current is flowing, let's say, then from this 5 volts, the current flowing through that resistor, through this here, through this 220 ohm dude, through this LED here, thank you, Mr. Holniak, this isolator, optical isolator here, and so this thing is actually turning on. It's inside a chip, you don't see the light, but it's turning on and turning on this transistor. So if there's current flowing through it. So then this transistor here turns on, which means it grounds out this thing, which means you get a ground over here. And if you actually followed all that garbage through, it turns out that a low here does get you a low there, but we're not worry about that. If there were no current flowing, which also happens a lot, like when the line is dead or when so if there were no current flowing, then this UART would get 5 volts just through this pull-up. Okay, so we're going to continue our current loop here. It goes through this here. It'll never go through this, D1 here, because you started at 5 volts, and these circuits don't go any higher than 5 volts. I mean, it's either going to go to ground or there's not going to be any current. So this D1 here it doesn't do anything. So you're going through this a guy here, you turned them on if there's current flowing, or didn't turn them on if there's no current flowing. You go to pin 5. Pin 5 comes back to here and goes to this open collector. So basically, this is the control. Is there current flowing or not? If this is grounded, from the UART, if this is grounded, then there's current flowing. If this is grounded only when the UART is outputting a 0. So it's a little confusing. When you're outputting a 0, there's current flowing. When you're outputting a 1, there's no current, which might seem backwards. The other thing that's confusing is if there's no current when you're outputting a 1, then the voltage is high. So it's very confusing. There's lots of inversions here depending, because with a scope you're usually not measuring current, you're measuring voltage. So it's all kind of confusing. But this thing is defined as a current loop. So if you're measuring voltage, be careful about what you're expecting, because, if the current loop is there, then it's a valid circuit, and you don't necessarily know exactly how many volts you would see. But in general on a scope, once you figure out what's going on, it has a typical problem that any UART stuff has. Like you're looking at this thing, you're trying to debug it, and it takes you a long time to figure out, oh, my bits are upside down and backwards. Meaning, you don't know if the UART's outputting the least significant bit first or the most significant bit first. You don't know if a voltage high or low, but those are the only options. There's not any more than that. So, you just kind of screw around with different interpretations. Send something that you know what you're sending and get your bearings. Okay. So anyway, that's how this works then. Again, there would be current flowing if this open collector here has a low output, or if the UART is outputting a 0. If the UART is outputting a 1, then there's no current flowing. And like you say, it's sort of like an amplifier of sorts, or it's also converting to current. But it is really, if there's 1 here in voltage, you're going to see a 1 here in voltage. It's sort of the A actually sort of makes sense as a symbol. We good? So that's the MIDI stuff. Current and cable flows when URTX puts a high or low. We talked about that. And does the D1 diode do anything? No. The D1 diode does nothing under normal circumstances. What is a D1 diode for? Well, it's for people that made their own cables and screwed them up. It's so easy to get the pins wrong that people often do them backwards. You don't want to burn out any chips. So if you accidentally cabled your thing wrong, then this D1 diode just makes it so that you're not putting reverse voltage across your optical isolator. Now, I will tell you a dirty secret. I deal with a lot of people that make cables, and they sometimes screw up. And you know what? You can buy nowadays, there's so many things out there. Right now you can buy an optical isolator that's exactly like this one, except it has 2 diodes in it, one facing each direction. So you don't care which way the current's flowing. If the current's flowing, then it'll turn on. So that's what I do. Because this other diode actually has to be a pretty big diode if it's going to, you know, anyway, it just isn't worth it. Plus, it's an extra part. But the mean thing about that is, so people make their own MIDI cable. They're cheap to buy. You can buy them for $3. You know, I'm not sure why you'd make your own, but hey, if you do make your own, maybe because you're converting to 3.5 millimeter or something. But they make a MIDI cable, and they know their MIDI cable's right because it works with their continuum. Well, what I didn't tell them is I cheated. I don't care if they make the cable backwards. It'll work either way. And then when they use it with other equipment, they call that manufacturer and complain, and it's actually not that manufacturer's fault. But anyway, yeah, so there's various tricks. There's lots of variations of the circuit. One of the very common variations nowadays that is really not compliant but is done a lot is to do 3.3 volts and to use lower current. But again, you know, that's just sort of natural, right? If you have a battery-powered thing, you don't want... now, the nice thing in the battery-powered thing is at least, say it's a sender, it's a controller, on this side, when the line is dead, there's no current wasted. But still, 5 milliamps is a lot. And so instead of doing that, you know, people sometimes don't use 5 volts, and people sometimes don't use quite the 5 milliamps current, but this stuff still works. Are we good? All right, so a bit more about asynchronous communications. So what is the actual data sent out of UART? Here, you got your 8 MIDI bits, okay? And if you were sending ASCII, I would say your 8 ASCII bits, even though that's doesn't make any sense, right? ASCII 7 bits. We always say it's 8 bits, but it's not. But UART, you know, there's all sorts of things that are 8 bits. Like there's an extended ASCII that has some symbols from other languages that is 8 bits. And then, of course, UTF-8, the Unicode, which is mostly prevalent, uses 8-bit parts. And if you only have a 7-bit encoding of 0 at the top, then it's really the same as ASCII. So it's sort of a superset. There's lots of different supersets of ASCII. For MIDI, well, we have 8 MIDI bits. And we'll talk about how those are divided up. And it's sort of divided up again as 7 bits and 1 bit, but we'll talk about that later. For now, we're just calling them 8 MIDI bits. They're going at 31.25 kilobaud rate. So there's 8 MIDI bits, but there's also a stop bit, a start bit ahead of time and a stop bit. Okay, that you need. So there's really 10 bits of data that's sent. Not 10 bits of data, 10-bit intervals. There's 8 bits in the MIDI, but there's 10 bits total. So 10 transmitted bits for 8 MIDI bits. And so that's 3.125, or we just say 3, MIDI bytes per millisecond. And that's a really important number, 3 MIDI bytes per millisecond. That number comes up over and over and over again. All right? Make sense so far? It's just good to know this stuff. It's not rocket science, really, but the nitty-gritty of MIDI. Oh, that sounds great. The nitty-gritty of MIDI, yeah. But the nitty-gritty here really does sort of matter, because there's lots of details in all of this that confuse people, and just something to know about. So, MIDI encoding. Oh, I should say, a common way that you see MIDI nowadays is that, there's only 2 lines here and ground connect on one end. So a common way to see MIDI done nowadays is with 3.5 millimeter cable. So the same as like your audio jack would use. And that works. Unfortunately, the MIDI standards group was so slow to come up with a standard that everybody had, the tip, ring, and sleeve. Well, the sleeve is always ground, but the tip and ring is this the tip or is that the tip? Well, it's halfway divided because everybody was starting to do this because there was no standard, and people randomly did different things. So now you have adapter cables. They remind me of the good old days of null modem cables, same issue, where it just swaps the two pins and stuff. Or you make your own cables. With the new continuums, or with the slim continuums, I didn't have room for these big MIDI cables, so I put in little ones, but I just send adapters with them that go to the big ones, so no matter what they got, it'll work for them. And on the input side, you can because I'd always done this thing where I didn't care how the cable was made. Turns out it'll work for anything. It doesn't matter what they have. On the output side, though, you got to know what goes on the tip and what goes on the ring. All right, so MIDI encoding. Let's talk about what's going on. First thing, we got a status byte. And the status byte tells you what is the following stuff. What's the data that's going to follow. Okay? So you have a status byte and then some data bytes. I'm using the words that they do. I'm not sure status is really a great word, but that's the word they used. And so, again, it's a standard. It's silly to come up with a new word that'll just confuse things. So we call this a status byte. The status byte has a top bit set. All data bytes have top bit 0. Status byte has two fields in it. A status code, that really means what kind of data. There's 8 different kinds of data that might be sent. And then there's a MIDI channel number. So I want to talk about the MIDI channel. What does that mean? Well, each channel can be polyphonic. So if you're going to have notes after this, you're telling it which MIDI channel are you on. They're encoded, of course, as 0 through 15, but unfortunately, the people that made the standard thought musicians were too dumb to know what 0 is, so they call them 1 through 16. So there's always this off by 1 thing that people get confused by. But anyway, MIDI channels 1 through 16, each one can have its own notes on it, can have chords on it, can have whatever you want on it. Each one is polyphonic. The reason there's 16 channels, the reason you always say what channel is the next note on, is because each channel can have its own timbre settings. So you might have one timbre that's some lead sound, another timbre that's some bass sound, or whatever. Say you split your keyboard. You might want to use channel 1 for the higher notes, channel 2 for the lower notes. And they sound different. Right? So that's the idea of MIDI channel. There's 16 channels. You usually don't split things 16 ways. But who knows? Maybe you have a DAW, right? And it's playing, and you're playing some orchestral music, and you want the violin sound on channel 1 and the tuba on channel 2 and whatever, so on and so forth. You can do it that way. Now, any channel can change its timbre on the fly, but if you're playing simultaneous notes that are different timbres, they have to be on different MIDI channels. Otherwise, you have no way of telling it this note is this timbre. Does that make sense so far? All right. By far, most MIDI communications is done on MIDI channel 1, or these bits 0. Because the simplest case is, hey, here's some notes. And you're not doing this stuff. So that's by far the most common thing. Okay, so then you have a status code, and it means what are the notes afterwards, or what are the things afterwards. So a note on has a status code of 001. Okay, so if a MIDI byte, if a status byte comes, so top bit set tells you it's a status byte. Top bit weren't set, it wouldn't be a status byte. It would be a data byte. And if you just connected, like if somebody just connected your synthesizer, somebody just connected MIDI input to you, you got to wait until the next status byte comes along. And when that status byte comes along, then you know what the data is. But before then, if you're just getting data bytes, you just ignore them until next data. So if you came in mid-conversation, that's okay. You just wait until the next status byte. So you got the status byte here. 001 means note on. Then you have a channel number. So if you have, say, a keyboard split, you might have all zeros here for one side of the split, all zeros and then a 1 for the other side of the split, or MIDI channel 1 and MIDI channel 2 is what that would encode. Or you just leave them 0 if you don't care. And then you've got data bytes. They always have the top 0. Now, what the data bytes mean depends on how many byte are they, right? After a note on, the first data byte is pitch. And pitch really means note number, keyboard key number. Their terminology is pitch, so that's what we're using. Pitch actually means lots of different things to well, you'll see in future lectures when we talk about psychoacoustics, pitch has very specific meanings, but anyway, it's MIDI note number. It's an integer where 60 is middle C, 69 is middle A. And that's where it comes from that in modern times, when we talk about fifth octave C, that's usually middle C. Where when you read your MusicN thing, I think their third or fourth octave were middle C. I don't know which one it was. Yeah, in any case, here we call the fifth octave C octave, just because 60 divided by 12 is 5. So this is what pitch you want to start the note. And then it's velocity. You know, how hard was the key hit? Really, how fast was it moving? And that's based on keyboards, on pianos rather, where you have a hammer that flies, right? How fast is the hammer flying? And the velocity has a value 1, and this is actually encoded 1. I'm not going to do this 0 and 1 thing. There's actually a 00001 in here. That's super, super, super quiet. And then 127 is fortissimo. What happens is people like loud music, and most people try their keyboards in a music store. You know, they go in there, they play each one for 3 minutes, whichever one they sound best at, they play. So in fact, almost all keyboards nowadays only use half this range or less. They only use the big numbers because they sell more, which is unfortunate. You know, makes it less accurate, but doesn't matter. Got to pay the bills. One of many historic unfortunate C's about MIDI that isn't really part of encoding, it's just of how it's developed. But there are systems and breath controllers and stuff that really go 1 to 127. They use all 127 different values here. Okay, so let's say you're playing a 10-note chord on a keyboard. There's such thing as running mode. Okay, and what does that mean? You don't need to repeat the status byte if it's the same as last time. So normally this note on would be a 3-byte message. But you don't have to send the running mode again. So if you say note on and you tell it's on channel 1, then you give a pitch and a velocity. If you got another note and you just, you know, a while ago sent a note on, you can send another pitch and velocity without sending the note again. It knows these pairs of bytes afterwards are new notes. And that's a huge deal, right? Because if you want to play a big chord, that's like, you know, how simultaneous are notes on a keyboard? They're spread out over, you know, quite a few milliseconds, but not that many milliseconds when you play simultaneous. And so, you know, if you took a ruler to it and pressed them all down, okay, maybe they'd all be at the same time. But if you're actually playing with human fingers, there's some spread there, but not that much. And they didn't want chords sounded arpeggiated or other timing problems if you're going to play a big chord on a keyboard. So that's why this optimization exists. So the note on, at the beginning here, you send, you say it's a note on, then you send pairs of numbers, pairs of bytes that are just the notes. And there can be dead time in between them. You know, they don't have to be instantly after each other, because that'll almost never happen. But anyway, you can just send note on. So that makes it very efficient to do keyboard music. Now, in keyboard music, most of the time, people are only playing the keyboard. They don't wiggle the wheels. They're not pressing pedals. They're just playing, especially if you're playing super fast. You know, if you're playing super fast and lots of notes, well, you don't have a free hand to be wiggling the, well, you know, you might be doing something with the pedal maybe, but that's pretty slow compared to what you're doing with your fingers. And so the idea is there's another optimization here, which is Midi Velocity 0. Okay, if you have a note on, I said here 1 to 127 is the velocity, but there's a special hack, a special optimization, sorry, that says if you put a 0 here, it actually means note off. So in general, if you look at the note off thing, it has a different code. It has to tell you which note number because you might be playing many note numbers, right? You have to tell you which note is it that is turning off now. And then you have an off velocity. How fast did you lift your finger? In the history of synthesizers, very few actually measure this. And if they do it so inaccurately. And even if they did it, you know, what synthesizer uses is information. Very rare. So the note off velocity is almost never used. Even in the eigenmatrix, where people can do whatever they want, and it's easy to measure velocities and those kinds of things, well, easy. If you're skilled with the Eagle matrix, it's easy to do these things. The minority of sounds actually do anything when you lift your finger, anything special. So there are some, but it's a rarely used option. So most keyboards don't use this at all. So the idea is that instead of having to send 3 bytes when there's note off, and say you're like playing lots of new notes and releasing notes at the same time, which could, there's lots of examples of that kind of stuff in keyboard music. Well, you could just send one note on, and then the pitch, say you're playing an A, so you say number 69 and velocity 104. Then sometime later, when you want to turn that one off, you say 69 velocity 0. And you don't even have to send a note on status byte again. Okay, so really in 2/3 of a millisecond, you can play notes. And for the case, keyboards are somewhat unique in that stuff can go by very fast, and people like fast music, at least in times, and the people may also very much care that the timing is right, because this is a real-time thing, so it's optimized for that. Now, if you're playing, I don't know, say you're playing continuum or something, you've got very different considerations, right? You're probably not going to be playing 12-note chords like you can on a keyboard. Instead, you want to know really fine pitch accuracy. So that, the encoding for the continuum is optimized in a very different direction. And I made that encoding myself, and it's really just standard MIDI. It's just, well, what do you encode in what order and when, and we can talk about that some other time. For standard keyboards, this is really great. So does that make sense? There's 2 different things here. There's the running mode, which means you don't have to repeat this, and then there is the Midi Velocity. Now, in USB MIDI, it actually, in this most serious case, or this most extreme case, if you're really playing fast on a keyboard, it doesn't have the running mode. It doesn't support that. So it's only 2/3 as fast as going through a standard cable. Most of the time, it just doesn't matter. It's good enough anyway. But if people tell you, oh, USB MIDI is faster because USB is faster, so they just fundamentally don't understand communication protocols. There's a real confusion here. And there's a reason why USB MIDI left out this thing, because if you always require the note on with every pitch and velocity pair, yes, your throughput's a little less, but it solves another huge problem. Say you have 5 different programs running on your computer, and they all like to spit out MIDI messages. Well, if you always require them to have the status byte with everything, then the longest MIDI message you see is 3 bytes. Some of them are 2 bytes. There are actually some that are only 1 byte. But, then everything can be mixed together easily. Now, if both programs are playing exactly at the same time, trying to play different pieces of music, well, that would be sad. But that's not usually what happens, right? People are running 2 different programs, and they're playing in this one for a while, they're playing in that one for a while. And to just make it easy to switch and not have running mode issues and other things, just blow it off. Just don't even do that. And so they had good reasons, and I don't argue with it. But I do have problems with people that are worried about MIDI speeds. It's not faster. So, next, we're going to just look at some of these other ones. Polyphonic key aftertouch. This is for early keyboards. There's very few that do this now, and the ones that do it aren't very accurate until, hey, this Osmos thing. We're working with a French company that will be accurate. They're using the same kind of technology we use in that I've been using in the Continuum. They're making a really good keyboard, but not ready yet. But polyphonic key aftertouch, what does that mean? Well, it's very sensitive to what you're doing after you've pressed down the key. And each note is independent. It's called polyphonic because each note is independent, so you have to say, oh, the middle C, the 60, and then give the new pressure for it. So you can update pressure as you're playing and have that affect the sound. Historically, that was expensive to implement, so most companies that were doing it stopped doing it. It also has this problem that if you're a keyboard player and you're not used to having that really affect the sound in an interesting way, then it actually sounds bad when you're trying it for 3 minutes at the store, right? And so it's like, uh-oh. So the manufacturers have made it harder, so you have to be a gorilla to really press it. If it's too hard to press, then it's just not that useful for anybody. And so eventually it sort of fell by the wayside. But people still want to say they have aftertouch, so then they made this channel aftertouch thing. And that just means all the notes on this channel. There's just really one overall pressure sensor. So some keyboards have that. That's a lot cheaper thing to measure. But yeah, it's not quite as cool as polyphonic key aftertouch. It doesn't require as much data because the MIDI channel, well, every note on that MIDI channel is going to be affected by it. All right, we're good. Thank you very much. I will let you go. I don't want to keep you too long. Sure.
So how are the exams going to be formatted? Is it going to be mostly like conceptual stuff they learn in lectures, or what?
Yeah, I'll give you a sample exam, and there are very few plug and chug questions. I have a few of them, but mostly it's just ideas from lectures. I'll also give you a subset of lectures that you actually have to study for the exam. I hate saying that because then people figure, well, I'll just blow off lectures until then. I mean, I'm hoping people are here because they want to do it, but realistically, it's just too much stuff, right? In a survey course, you get a little bit of everything. It's just too much. So I will say, which lectures to concentrate on. I haven't written the exam yet, so can't do that yet, but I'll do that.
So it's going to be mostly stuff from lectures, right? Maybe a little bit from labs as well?
There'll be a lab question or two, maybe, but I don't want to do too much because I don't want you to have read every, have to have memorized too much stuff. So I usually try to have a pretty generic lab question. Like if you've been going to lab, it's kind of a giveaway. And then there also is potentially from homework, but you already answered these homework questions. And again, to try to protect against people that are just copied somebody else's homework or something, I can try to do that. But I'm hoping by this point you're actually interested in this. So I'm not trying to do too much of that. So yeah. So but I will give you more information on that. The only useful thing in the exam is writing the cheat sheet. So make sure you write your own cheat sheet. Don't just get one from somebody else, because you're going through the exam itself is just a waste of time. I mean, the skill of doing well under time pressure and answering a bunch of questions is not a useful skill, except for college. So yeah, make sure you write your own cheat sheet. That's good use of your time. Thanks. Oh yeah, absolutely. Thanks. Oh yeah. All right, thanks.
See you next week.
Yeah. And this, even if this weren't on the exam, this is just sort of good stuff to have seen and look over. And I mean, in a survey course like this, there's no way that anything I teach in this course you're going to have learned enough about to really be an expert at it.
Just to get us exposed.
Yeah, just to sort of see all this stuff. I mean, this course is really what I wish I had when I was a student. So.
It's honestly a nice change from a lot of the other courses. It feels like partly a history class, but also there's a lot of cool technical stuff.
It's a lot more like a lot of graduate seminars would be. It's less structured, and also the grading is more like that. And the worry for me is like, well, if people are looking for an easy A, I have to be careful about that, and that's why I have to give exams. In fact, I'm required to give exams. But realistically, most people that take this, on your resume, I don't know, if you're just resume building and you actually have no interest in it, it's sort of a weird class to take. So in that way, it works out okay.
Yeah, all my last semester classes are like these kind of classes, so it's just really nice, just like.
Yeah. Well, you finally get to the point where instructors assume that you actually are interested.
Yeah.
Which is a total difference from so much of school where you're being, threatened into working hard.
And it's just nice to have like a smaller class as well, because I'm just so used to having like 200 people in my classes that like it just feels more like you're just going to lecture.
Well, when I took over this class, originally I had like 7 or 8 in a semester, and I really liked that. But for a big department like this, to teach a class that isn't, a mainstream of funding class, but now it's good.
A lot of people want to take because it's not like, doesn't have like the zinger where it's like, oh, machine learning, artificial intelligence.
Yeah.
People just.
Yeah, and a lot of people just, it's just they played, an orchestra as a kid or something, or they played in band, and just sort of something interesting and something to do with signal processing, and it's a change, as you say, a change from the more mainstream stuff. But I'm just glad to see it too, because I mean, traditionally, university wasn't just job training, and actually people that come out of here do just fine. Just because people have told me that I went into things without music at all, said, oh yeah, this or that from the class was actually really useful to them. So, You know, I think it's good. I mean, in the end, the signal processing and stuff, especially in the second half of the class, is all pretty standard stuff. Like, it's not signal processing for the sake of signal processing. It's sort of traditional methods, you know, used in music. So, cool. Thank you. We'll see you. Thank you.